We learned about the quantum phase space in the last video, but I had left it in between and didn't talk about in detail about Wigner functions. So, Wigner functions are quasi probability distributions which provide a phase space representation of the quantum states in continuous variable quantum computing paradigm. It helps us to simultaneously analyze both position and momentum information. This is particularly useful in systems where both the position and momentum are important, such as in quantum optics and quantum information processing. Wigner functions work in conjunction with the traditional probability distribution functions. In the classical limit, that is, for large quantum number limits, the Wigner function reduces to the classical probability distribution. And this property, in fact, it ensures that the Wigner function provides a seamless transition from quantum to classical mechanics, making it a valuable tool for understanding the classical behavior emerging from quantum systems. Now, let us compare both the classical probability distribution functions and the quantum and the Wigner functions. So, in classical mechanics, the probability distributions describe the likelihood of finding a particle at a particular position or with a particular momentum. These distributions are usually non-negative and integrate over one. So I would write it as normalizable over the entire phase space, classical phase space. In contrast, the Wigner functions can take negative values, so there is no such restriction, and sometimes they can be not normalizable. So both of these things are uh, to be taken into consideration, and that is why Wigner functions are also called as quasi probability distribution functions rather than probability distribution functions. Now, even when these kind of issues are there with Wigner functions, we can still work with them, and I'll come to that point. Now, Wigner functions, they provide a convenient way to visualize quantum states in phase space, where each point represent corresponds to a unique combination of position and momentum. And this gains allows us to gain insights into quantum states spread and shape in the phase space, providing a more complete picture than the traditional wave function representations that we usually study in quantum mechanics, which typically only provide information in position, either in just the position space or just in the momentum space. So the quantum probability distribution functions, uh, let us also write them here. They are also non-negative and no normalizable, just like classical one. But this classical probability distribution functions can give us information in both x and p phase space. This also gives us information of the x and p, the Wigner function, but this does not give us probability this quantum probability distribution function. It either gives us the probability distribution function in position or the momentum space. It can't be used in the quantum phase space, and that is why we need something like the Wigner function. Now, coming to the marginals, so this being the despite Wigner functions being having negative values and sometimes not normalizable, it still have some useful information in terms of the marginals. That is, the Wigner functions, let's say we represent it by W, and they are always dependent on X and P values, and also can be converted to be dependent on alpha and alpha star value of the particular state. on the quantum phase space. Now, if I integrate this Wigner function with respect to p, I will get the marginal probability distribution function for x of that particular state. And if I integrate it with respect to x, I will get a marginal probability distribution function. Let's write it in this way. For that particular state, in uh, the probability distribution function for the momentum. So the marginals are probability distribution functions of uh, they are the probability distribution functions, and they can be extracted out from the Wigner function, and hence Wigner function plays a role here. Also, Wigner function has a close relationship with quantum operators. That is, the expectation values of operators can be calculated directly from the Wigner function, providing a direct connection between the phase-space dynamics and quantum operators. This allows us for the calculation of observables and the study of the behavior of states in phase space. So, in summary, Wigner functions they provide a unique and powerful tool for understanding quantum systems by providing a phase-space representation that bridges the gap between classical and quantum mechanics. While it is having negative values and non-normalizable, but its ability to capture both the position and momentum information simultaneously makes them an invaluable tool for quantum mechanics in phase space. So, I will just introduce a few notations. We will denote the Wigner functions by this particular capital W, and this W will be dependent on x and p values of the state, and they can also be represented as being dependent on alpha and alpha star values of the state on the phase space. To understand the general mathematical expression for Wigner function, I will like to give you some motivations and understand why we define the Wigner function in the way it is defined mathematically. So, to understand that, we need to understand that the averages or expectation values they hold a lot of importance in quantum mechanics because they are something of a meaningful result in the quantum mechanics. Operators, that is x cap, p cap, h cap, etc., they do not themselves hold any value as such. So we will try to obtain the average of an operator, which is representing a physical observable using different approach. So consider that we have an operator O cap, which is a function of A cap and A cap dagger. So it can be, for example, A dagger A, just like the N cap operator, or A cap plus A cap dagger by 2, just like the X cap operator, and so on. So in general, I'm writing O cap as an operator, which is a function of A cap and A cap dagger, where A cap is equal to X cap plus IP cap, and A cap dagger is equal to X cap minus I P cap. Uh, a classical version of that can be given as O, a function O, which is dependent on alpha and alpha star. So I correspond alpha as a scalar which corresponds to the operator A cap, and alpha star as a scalar which is representing A cap dagger. And we call this O as a classical analog of this O cap. Okay. Now I can write this O, which is dependent on alpha and alpha star, as integration d square beta. By d square beta, I mean I'm integrating on a 2D plane. So this is surface integral d square beta. I'll explain it what I mean. Alpha minus beta o beta beta star. Actually, what we are doing here is a complex integration. So that is why I wrote d square beta. So because these alphas and betas are complex numbers, we are talking about of a complex plane where we have a real part of alpha and imaginary part of alpha or beta, whatever complex number is there, and we are integrating in this complex plane. So that is why I wrote d square beta, and this delta is the direct delta function, and O is uh, a function which is dependent on beta and beta star. Now, this is very similar to how we write any function f x dash, yeah, in the real sense, in the real numbers. F, a real function f x dash is equal to integration dx delta x minus x dash f of x. This is just the definition of the direct delta function. So I just what I did here is generalize the direct delta function for in the complex plane. Okay, so okay, your alpha is equal to x plus ip, and alpha star is equal to x minus ip. Okay, so here, as I mentioned, this delta is a complex direct delta function. What does it mean? So consider this alpha is equal to alpha dash, the real part of alpha, and alpha double dash, the imaginary part of alpha. Then some complex direct delta function delta alpha means that I have this complex plane alpha dash and alpha double dash, that is real and imaginary part, and I have f of alpha, the complex function, scalar function dependent on alpha. Then we say that the complex direct delta function is something like this, which is at a point alpha. It is similar to saying that the real delta function f of x lies at x, sorry, delta x. So this is how they are related to each other. Now this delta x can easily be written as delta alpha can easily be written as delta alpha dash delta alpha double dash. And we know from the Fourier transforms that any direct delta function delta x can be written as 1 by 2 pi integration dt e raised to I tx, isn't it? Yeah. So similarly, we will use the same idea and write delta alpha, the complex direct delta function, as 1 by 2 pi integration d of x e raised to I alpha dash x times 1 by 2 pi integration dy e raised to I alpha double dash y. Okay. Now what we will do is I will consider some gamma which is equal to minus I times x plus iy by 2, such that this is equal to y by 2 plus I into minus x by 2. I call this as x dash and this as x double dash. Pardon me, I'm doing this because the calculations become easier with this. Uh, or, sorry, I call this as gamma dash and gamma double dash, the real and imaginary part of gamma. So, in that case, alpha gamma star minus alpha star gamma is equal to alpha dash plus I alpha double dash into gamma dash minus I gamma double dash minus alpha dash minus I alpha double dash into gamma dash plus I gamma double dash. I will open it up, do some manipulations, and at the end of the day, this is equal to I alpha dash plus I alpha double dash y. I alpha dash x plus I double alpha double dash y. Okay, and I can now also say that dx dy, the element dx into dy is equal to 4 times d2 gamma. So therefore delta alpha becomes, so this was delta alpha, it becomes 1 by 4 pi square, 1 by 4 pi square integration dx dy, right, dx dy e raised to I alpha dash x into e raised to I alpha double dash y, e raised to I alpha dash x e raised to I alpha double dash y. So now what I will do is replace these. So this becomes 4 by 4 pi square integration d2 gamma and I alpha dash x plus I alpha double dash y, double dash y is nothing but e raised to gamma star alpha minus alpha star gamma. So we reduced this delta function, delta alpha, in this form 1 by pi square integration d2 gamma e raised to gamma star alpha minus alpha star gamma. Okay, so now this will be very important. So now let me use this thing now. So if you recall, we had written that O in alpha star was equal to d2 beta delta alpha minus beta O beta comma beta star. Yes, where I can now write delta alpha minus beta as equal to 1 by pi square integration d2 gamma e raised to alpha minus beta star gamma minus alpha minus beta gamma from this result. So the quantum mechanical version of it, the expression should be by the analogy d2 beta delta cap a cap minus beta o beta comma beta star, where delta cap a cap minus beta is equal to 1 by pi square integration d2 gamma e raised to a cap minus beta dagger star gamma minus a cap minus beta gamma star. And then this is equal to 1 by pi squared integration d2 gamma e raised to beta gamma star minus beta starred gamma e raised to a cap dagger gamma minus a cap gamma star. So this is a very familiar uh, notation. D2 gamma e raised to beta gamma starred minus beta starred gamma. This is nothing but d cap gamma. Look at the expression for the displacement operator that we described earlier. This is the exact same thing. So this is the quantum mechanical version, and this is the classical mechanical version of the operators. So I just wrote them in a different form here, which is very useful in understanding the later parts. Now, as I said earlier, this operator OCAP doesn't have any value by itself. So, what is the average of this operator? So, the average of this operator is equal to 1 by pi squared integration d2 beta delta cap a cap minus beta o beta comma beta star. This is what it is. And we know that averages can also be written as trace of the density of matrix times the operator itself. So this can also be written in this way. This is a definition, general definition. You can check any textbook for this. So now what I define a Wigner function as, finally. So now that we have got this expression, I define Wigner function as this particular function, the expectation value of this particular operator. So delta cap a cap minus beta, expectation value of it, I define it as the Wigner function. And it is also equal to trace of rho cap delta cap a cap minus beta. So this is the definition of a Wigner function. I know it looks scary, but we will understand once we will calculate the values of the Wigner functions. In some textbooks, you will see that the Wigner function is also defined as 1 by pi into h bar integration minus infinity to infinity x minus y rho cap x plus y e raised to 2I py by h bar dy. Uh, if I write rho in the pure state, then this can be written as psi psi. So this can also be written, the Wigner function, as x minus y psi into psi x plus y e raised to 2I py by h bar dy, and this will reduce to psi starred x minus y into psi x plus y e raised to 2I py by h bar dy. This is another way of writing a Wigner function, but I'm not going into this particular thing because this is easier to follow, and also it gives a very good understanding in the in the physical picture, and also the physical significance. One more way we can write the Wigner function and I'll write it for the pure state, is that if I replace the delta cap function, then this w beta comma beta star or alpha alpha comma alpha star, let me write it as alpha comma alpha star, it will be better. Alpha comma alpha star, it is equal to 1 by pi square integration d square d2 gamma e raised to alpha gamma star minus gamma alpha star psi d cap gamma psi. What I just did is I replaced this delta cap equal to this expression, and I took the expectation value of it. So I just took the expectation value of it, right? So I will get this is equal to psi here. So psi will go inside here, and it gives me the expression of the Wigner function in another form, which is useful to us. So this is another useful expression of the Wigner function. Now there is a you can, if you want to say what a Wigner function is, or to express it to someone in verbal form, then it is nothing but the complex Fourier transform of the average of the displacement operator. I know it's a mouthful, but this is how a Wigner function is defined mathematically. Now there is a one-to-one correspondence between Wigner functions and density matrices, but I'm not going to derive it. You keep it in mind that there is a one-to-one function relation between them, and that is why they can be replaced with each other. The density matrix and the Wigner functions, they can be. So that is why also Wigner function has all the information that is required about a state in the continuous variable quantum computing paradigm. Now, now what we will do is we will calculate the Wigner functions of particular states, the Fock state, the coherent state, and